Hey guys, welcome back. Okay, this is mostly going to be a design episode. I don't know that we're going to do a whole lot of coding. I think we might do some at the end. But before we get started on that, what I want to talk about is a couple more delete functions, actually 4 more, that I missed in the last episode. So you can see we've got 8 altogether here. We need another 4 more delete functions. We got all the new functions. Now you might think, well, we've got enough, don't we? I mean, geez, we've got a ton of these things. But there actually are some more, and I missed them because these were recently added. These are part of the C++ 14 specifications. I've never used these in my life. I'm not sure how many people have, because by default, actually, they don't do anything. By default, these functions actually end up just calling the regular delete function. I'll show you what I mean. But let's put them in for, just to have them in for right now. Operator. So these are the delete functions, and they start with the void, the pointer. And let's see, then there's a size. So that's what the other one looks like. Okay. By default, what this does, if you call this, if you provide a size, it simply ignores it and calls this function right here. It just directly calls this function, drops the size thing. So it really doesn't really do anything. The reason it's there is to provide a basis for easily overriding that function in case you want to customize it. So that's the point of it. The other one is the same thing. Delete size t, but it also has a no throw. Like such. I think that's right. Yeah, I believe so. Okay, so those are the 2 that we need, and then of course I'll just copy those, bring them down, and we'll put in the array versions as well. So there you go. That's the 2 that we were missing, and I will put these kind of up here with their counterparts so that they're in the right place. And then we'll go ahead and throw these into the memory manager class as well. That's going to go here. Like such. And we'll drop that in, and we'll drop that in. I never did look up that key command to reformat stuff. Somebody tell me what that is, to auto reformat your code. All right, there we go. And I'm not going to bother to test these, at least not right now. We may or may not override these. I don't really know what we're going to do with them yet. We may just do the same thing we did before and drop back to the or do what its default and just drop back to the regular delete. But the specification says that if you override this delete, or sorry, the regular delete, then you must also in fact override this one. And same thing for the array. Sorry, we gotta put the arrays in, don't we? Like such. All right, so there you go. That's what I missed on the last one. And again, my apologies. I kind of was unaware. It's not that I was unaware of them. You know, when you read the specifications, there's a lot of new stuff that you're reading through, and sometimes not all of it really sticks, and that's pretty much what happened there. I kind of forgot about them because they're not really something that I would personally find useful, so I didn't really pay much attention to them. But we do need to deal with them as overrides of the other deletes. So yeah. All right, very good. So I want to drop into Word for a minute. So I have our list of stuff up, and I want to talk specifically about a couple of things in here. This one right here, list of memory pools that is required by the memory manager class, and list of blocks which is required by the memory pool class. And also, somewhere in here should be I didn't put it in here. The defragmentation, the auto defragmentation functions, which should be handled by, let's see, that probably should be handled by the memory pool class. Let's put that in. Defragment memory blocks. So that one right there. Okay, what I wanted to mention about the lists and also resetting of pointers as caused by the defragmentation functions. We're working here under some pretty severe limitations that most programmers don't have to deal with. The first limitation we've got right now is we cannot use dynamic memory because that's what we're setting up here. Of course, there's the built-in dynamic memory handlers of the operating system and the stuff that's built into C++ that everybody uses when you're writing spreadsheet programs. And they don't have to worry about this thing. It's all built in, right? But we don't have that option. Because we have a custom memory manager, which we need because we don't want to use the operating system's default stuff for the most part, we don't really have access to dynamic memory. And what that means is creating a list of blocks where the list of blocks is a variable number of blocks, or the list of pools is a variable number of pools, is very difficult because in order to create a list of variable size, you almost have to have dynamic memory, and we don't have dynamic memory yet. So that's a limitation that we have, and we're going to have to talk about how we're going to get around that a little bit later. The other one that we don't really have at this point are pointers. I'll talk about the relationship between pointers and dynamic memory in a minute, but we want to use smart pointers. Now pointers are built into the language, okay? The original C version has raw pointers, which are great. Now, of course, pointers are just addresses into memory. They could be addresses into a stack variable, or more commonly, they're addresses into something that's defined dynamically on the heap. So you've got raw pointers, but raw pointers have some pretty significant problems. That's where you get your memory leaks from. When you lose a pointer, or for whatever reason a pointer goes out of scope or is destroyed for any reason, but you forget to delete the memory that it's associated with. So there's no longer any way to access that dynamic memory. The only way to access dynamic memory is through a pointer, right? There's no other way to get to it. So if you lose that pointer, you have no way to get to that dynamic memory anymore, and it becomes a memory leak. The other one that can happen sometimes is the other way around, where you have dynamic memory that you delete, but you forget to kill the pointer, basically null out the pointer. And that's called a dangling pointer, where the pointer is pointing at nothing. And if you try to put something there, you could end up overwriting something else. For example, if I create some memory, have a pointer to it, delete that memory, and then create some new memory, that new memory might end up where that old memory was, but the original pointer, if it was never taken out, or if it's pointing even worse, something into the middle of that new memory, you'll be directly overwriting something that you don't mean to be overwriting. So that's a dangling pointer. Now we have the additional complication of memory that moves, which is not something that most people have to deal with. So when we have moving memory, we got to move our pointers with them. So that's a third thing that we got to deal with pointers. So there's something, there are in the new specifications of the language as of C++ 11, a new set of pointers. So yes, there's a new set of smart pointers that are built into the language. And there's basically 4 of them maybe, if you count one of them that no one's supposed to use anymore. The first one that is deprecated is the auto pointer. So with an auto pointer, the idea is that it'll automatically destruct when the pointer goes out of scope, meaning that the dynamic memory associated with that pointer will automatically be destroyed. Auto pointers are now deprecated. You don't want to use them anymore. So basically, ignore auto pointers. The upgrade to the auto pointer is the shared pointer. So a shared pointer is very similar to an auto pointer in that if the shared pointer goes out of scope or is destroyed for any reason, the associated memory will be destroyed if and only if there are no other pointers pointing at that memory. The way this works is through reference counting. So if a piece of dynamic memory is being pointed at by, say, 3 pointers, it'll have a reference count of 3. And if one of those pointers goes out of scope, it'll drop the reference count to 2. And it'll continue to do that. And if the reference count ever goes to 0, then that dynamic memory itself is destroyed. And that's a pretty good idea. That's pretty brilliant. That's similar to what we're going to be doing with our pointers. So another one is called a weak pointer. A weak pointer is very similar to a shared pointer, except it does not increase the reference count of the memory block. And you might ask yourself, well, why would I want to do that? Well, there's reasons for it. It has to do with undestructible blocks of memory where 2 pointers are pointing at something, and if they both go out of scope sort of at the same time, you can't ever destroy that memory. It's a little bit convoluted. So the fourth one, the last one, is the unique pointer. A unique pointer it's similar to a shared pointer. It's got the same idea, except you can only have one pointer assigned into the memory, as I understand it. So yeah, I'll leave it at that. I mean, these things are kind of complicated. You can look them up if you want to. Yeah, I don't want to get too much more into the built-in pointers. Now, the question comes up, well, why, if we've got all these, we've got raw pointers and we've got these 3 smart pointers, why are we not going to use them? And the answer is specifically because of our design decision in the memory manager class to defragment the memory. If the memory moves, there's no functions in those smart pointers to move the pointers with them. Now, we could probably go in and override and overload some stuff to try to get them to do that. My feeling is that that's such a major change to those things that we pretty much might as well go ahead and roll our own. And I think for the purposes of what we're going to do, we're going to build something similar to the shared pointer. I don't know that we're going to need to build a unique pointer or a weak pointer. We may want to do, but we'll leave it till later if we end up needing them. Especially the weak pointer, there are circumstances where you might end up with that situation where you can't destroy a memory block. And if we end up with something like that, we may end up having to build ourselves some weak pointers. It's very simple to do. It's not that hard. It's all a matter of who's updating the reference count, basically. Who's allowed to update the reference count, who's not allowed, and all that kind of thing. That's pretty much all there is to it. So yeah. Okay, guys. So those are the major limitations we're working under, and under those limitations, building a list of stuff is pretty difficult. I struggled with this quite a bit, actually, to be honest. And I started to think about, well, we could use pointers to do these lists. We could do a linked lists, which inherently use pointers to build these things. I think what it comes down to, gang, is that we really need to keep separate the 2 concepts of pointers and dynamic memory, or heap memory if you prefer. These are 2 separate concepts, but they're very intertwined. And they're so intertwined that it's almost difficult to keep them apart. But we want to keep it to 2 different things, because we're going to have classes that are separate, and these classes should have specific responsibilities related to those things. So a pointer is simply an address into a block of memory, into another variable, whether it be a heap variable or a stack variable. That is all it is. Okay. Now, yes, we will be dealing with reference counting, and yes, we will be dealing with moving those pointers, and dealing with auto destruction and all that kind of stuff. We're going to be dealing with dangling pointers and memory leaks and all that kind of thing. But at its core, all a pointer is an address into another variable, and we want to keep that in mind. That's important. Anything that has to do with modifying that address should be taken care of by our smart pointer class. On the other hand, dynamic memory, heap memory, is dealt with by our memory manager class. Now, it's going to have no knowledge of pointers. It should not know anything about the pointers that are pointing into it. That's the responsibility of the smart pointer class. So if you keep those concepts separate, things kind of simplify. They are linked together, obviously. I mean, when you do a new statement, you're building something on the heap, But what are you returning? You're returning a pointer, right? So, I mean, that's the link between them right there. Those functions, those new functions. And by the way, guys, since we are going to be using smart pointers, there's actually going to be no need to necessarily delete them because they will auto-delete when they go out of scope. However, we're still going to implement the delete functions because programmers will use them anyway. We don't want to say, okay, you can use new, but don't use delete because the program will handle it itself. If they want to use delete, we'll let them use delete. And there probably will be times when we want to use delete to delete something before it goes out of scope. So yeah, anyway, let's continue on. So with those two concepts in mind, those two separate things, memory manager, smart pointers. What are we going to do when the memory manager moves memory? When the memory manager moves memory, we need to inform the smart pointer classes that their addresses have potentially changed. Now, the memory pool classes, or the memory manager class, as we have stated, don't have any knowledge of the pointers. So how are they going to send some kind of message over to the pointer classes? Well, we're going to do exactly that. We're going to send a message. We'll use some sort of messaging system to say, hey, pointer class, this pointer with this address. Now the memory manager is going to know the old address and it's going to know the new address. And we're going to say, if your pointer has this address, you need to change it to the new address. And that's how we're going to handle that. That's the only thing the memory manager class is going to do with regards to pointers, as far as letting them know when something has moved. Because that's the memory manager's class responsibility, is to move pieces of memory around. That's one of its things. And then it'll send that message off and then forget about it because it will have no further knowledge of how to do that. Okay. Now, here's the tricky bit. Here's the whole reason why I decided we need to do a talk about stuff rather than actually do a whole lot of coding in this one. How in the world are we going to handle that? Because think about it. What are we going to have? We're going to have an address. We're going to have the old address and we're going to have the new address. Pointers don't work that way. You don't send an address to find a pointer. You use a pointer to find an address. So it's backwards, right? So how are we going to handle this? We're going to have some sort of list. And here's another list again, guys. We're going to have a list of all the pointers and their addresses somewhere so that we can look up the address and get the pointer. And to do that, we're probably going to have to use, since we don't have dynamic memory and we don't have regular pointers, we're probably going to have to do something involving a pointer block of memory. Now this gets a little bit tricky too. So if I have a block of memory that I set aside just for use for pointers, there's a couple of problems with that. One, it limits us to a specific number of pointers. It's like, say we say, well, we want to put in 65,000 pointers as a possibility. If they go above that, now you've crashed your program, right? But we can't have dynamic memory. We can't do that because we don't have that ability yet. The second problem, did I explain that first problem adequately? So we're going to have an upper limit to the number of pointers that will be allowed to be alive at any given moment. Because we need a list, right? We need that list. Otherwise, we're not going to be able to find the pointers that we're looking for when we have this address. The second issue is that pointers aren't necessarily guaranteed to always be the same size. I think in almost all cases they are, but function pointers, for example, are a different size than integer pointers, or they can be a different size. Whether they are or not, I'm not really sure, to be honest. The specification here is a little bit tricky, but basically there is no guarantee that a pointer of one type is exactly the same size as a pointer of another. Now you think they would be because everything points to a memory address, but function pointers are a little bit different. And we want to be able to use function pointers. So what we're probably going to do here, what I'm thinking we're going to do to handle this, and this is all going to be handled in the pointer manager class. The pointer manager class is going to have our list of pointers and their addresses, so that we can look up an address and we can grab the pointer to it, and then we can change that address. What I'm thinking we're going to be doing here is using a list of pointers to pointers, and this may be using raw pointers rather than any kind of smart pointer, because we can't use smart pointers to implement the smart pointer class. This will be the one case where we have raw pointers. Now, pointers to pointers are guaranteed to be the same size because they're all the same kind of thing. That being the case, then we don't have to worry about fragmentation, because if you delete a pointer, you can simply stick another pointer in its place, and it'll fit right in. There's no need to move them around, as long as we don't overfill the block of memory that we're using to store those pointers. That should work. Now, I don't love the idea of a limited number of pointers, but it can't be helped as far as I can tell. Without the ability to use dynamic memory, we can't grow this block of memory at all. So we're just going to have to set it. We may end up eventually setting it as a variable size so that we can say, we can put it into maybe some sort of INI file ultimately that can be read in, and so it can be set from outside the program in case they need to make it bigger. That would require a recompile though, I think, so that may not work either, because we're not going to have the ability to do it dynamically. So yeah, I mean, there's a lot of trickiness. There's some trickiness to the pointer manager that I still haven't quite decided how we're going to handle. The basic goal here, guys, is to get out from under this limitation as fast as we can, because it really is causing us a great deal of problems. If I had dynamic memory and smart pointers, we'd be done with this 5 episodes ago. so yeah, but unfortunately I don't have them, so we got to get these done. So yeah. All right. Okay, guys, so I've yapped on quite long enough. I do want to do a little bit of coding here, because I'm doing a lot of talking and not a whole lot of coding in this episode, or not just this episode, but this series in general. But I mean, there's some of that's necessary. We all need to be on the same page as far as where we're going. So I don't have anything coded up at this point. You can see I only have the one Visual Studio up. I don't have my scrap one up. So we're just going to play this by ear, which is probably always a dangerous thing. So let's talk about the memory manager class. Right now we've got a constructor and a destructor. What functions do we need in the memory manager class? So let's take a look at our thing. We want to handle the overall memory pool. We want a list of memory pools. We want to allocate new memory pools, add pools, and delete pools. So query the number and specific status of a particular memory pool. So these are all functions, pretty much this down, that are going to be public domain functions, right? Also, the memory manager class is going to be the only interface to the rest of the program. Everybody else is going to come in through the memory manager class. So really, anything down in here that we want to do, or down in here that we want to do, has to come, if it's going to something that's going to be handled by something outside of this class structure, we have to have a kind of an interface in here to get to it. So anyway, at the moment, what we want to talk about is the adding of pools. So what do we want to do? We'll make it a void for right now. Add new pool. We'll just make it the simplest kind of function that we can make it. And we're going to throw these up top. And actually what I'm going to do is put a double thing here. This will signify that these are global functions below this line. Okay. So I don't necessarily want to implement these quite yet. But I want to get them set up. Let's get on our... Okay. So we'll need to be able to add new pools. We'll also need to be able to delete a pool. So let's do that. Okay. And we'll create a definition for it. All right. So obviously we're going to need parameters in here. We may want to return something rather than a void, but we'll figure out the specifics later. For right now, we just want to kind of add in the stuff that we know we were going to need at some point for this to work. Additionally, the memory manager class, once per frame, is going to need to be able to defrag its pools. So let's put that in, defrag pool as well. All right. And let's drop that into the memory manager class, like such. Let's see. Let's take a look at our design document here. So we're allocating new memory pools, add pools. It's kind of the same thing, isn't it? Let's take this one out. That's actually kind of redundant. So allocate new memory pool. Well, you know what? No. Yeah. Never mind. I kind of know why I made them two different things, because allocate the new memory pool means to actually set up the memory for it, and add memory pool means to add the pool to the list of pools, but it's the same thing. Okay, it's a little bit ridiculous. Query the number. Okay, so let's do that. We got to query the number and specific status of a particular memory pool. So that's something we could add in, right? So void query pool as well. So we'll just set that up as a function. Oops. All right, and there you go. Okay. I'm going to get rid of some of this stuff that we don't need anymore. We can always pull it back up later if we need it. I may need, yeah, I'm going to need probably in here, in the global manager, we were going to need memory manager class. Memory manager. So let's put that in so that the entire program has access to this. There we go. And to do that, we need to include it. Like such. That should do it. There you go. So now we should have a global access to the memory manager class through memory manager right here. And that's what we want. Okay, let's pull up the block class and the pool class as well. So these are just, yeah, these are just skeletons. Okay, what else do we need to handle here? So let's deal with the add blocks and delete blocks. Now remember, we are going to run everything through the memory manager class. The memory manager class is the only one who's going to have access to this stuff. So anything that needs to be done by the program at large has to be done through the memory manager class. So this is where we're going to set up void add new block. Now, yeah, do we really want to do that? Come to think of it, no. So add block and delete block, guys, are going to be handled by the new functions, new and delete. That's how we're going to handle those. So I'm not going to make an interface in here for those. So really, guys, at least as far as I can think of right now, and this may change in the future, but that's our interface. We've got the ability to add a new pool, delete a pool. We're going to defrag the pools. This one, I can think of better ways to do that, but we'll leave it there for right now. And we can query the pools. And of course, we'll have parameters in here, which will define which pools we want to use. The defrag probably won't. And that's it. We don't need any function to add a block or delete a block, because that's going to be handled by the new and delete functions. Which, by the way, guys, actually, we're probably going to add some new ones in here, if you want to know the truth. I'm going to overload these guys with stuff like this. Void star operator new. You'll need a size, but you're also going to need a pool ID of some sort. So I'm going to, for right now, I'll call it an int. I don't know that it's going to stay an int, but pool ID, something like that. That's going to give me a warning, because I think it should actually almost give me an error, come to think of it, unless there's something it succeeded. Huh, interesting. Let's see. I wonder if one of these actually ultimately ends up being an integer. If that's the case, what happens if I actually define it? Oh, for God's sakes, would you come here? God, stop being a pain in the ass. Let's see. This shouldn't give me any grief. Yeah. Yeah, it's fine. So yeah, I mean, we're going to be end up doing stuff like that, where I'm loading the operator new to actually specify the pool that I want the block to go into. We'll be doing stuff like that. Which brings up the point of, well, what do we do with this when we don't specify a pool? And that's a good question. I guess I could probably address that for just a minute. I'm going to do int default pool ID, like such. So in the cases where you do like a regular operator new, where you don't define which pool you want to go into, it'll pick up the default one, and we'll by default make it the first one. But that can be changed later on. It might be something that we stick up in here. Okay, guys. Anyway, that's far enough. That's actually further than I really wanted to talk about. But so yes, I will stop here. What I want to do in the next episode is start dealing with these two: add new pool and delete pool, so we can actually get some memory set aside, ready to go for the memory managers for use. So yeah, possibly even start thinking about overriding these new functions to set up blocks inside of our memory pools. So yeah. All right, so we'll handle that in the next one. That should be an interesting bit of coding that we're going to get done. I think we're set up for it. I think we've got all the concepts we need down, and that'll be a long way in getting us towards at least getting out from at least one of these limitations that we've got on ourselves. There's more to come. So yeah. All right, so we'll take that on in the next episode. So I will see you guys in the next one. Thanks a lot.